General relativity, step by step. I've got a vector v and I've spent quite a lot of time decomposing it into its components like this, plus v2, I'll just do it in 3 dimensions, plus v3e3. And now if I get a w expressed in covariant form, w1 omega 1 plus w2 omega 2 plus w3 omega, oops, looks a bit suspicious. Let's try again, w3 omega 3. And I've chosen the omegas such that omega I dot ej equals 1 if I equals j and 0 otherwise. Spent quite a lot of time fooling around with that. So it's called a conjugate basis. Now what I'm going to do is if I want to get w dot w equals w1e, no, it's easy to get these things wrong, w1 omega 1 plus w2 omega 2 w3 omega 3 dotted with itself, dot w1 omega 1 plus w2 omega 2 plus w3 omega, looks like a v, doesn't it? w3 omega 3 equals w1 omega 1 dot w, I'm just going to expand it, w1 omega 1 plus w1 omega 1 dot w2 omega 2 plus all the other terms, w1 omega 1 dot w3 omega 3 plus all the other terms all the way down to w3 omega 3, w3 omega 3 up there. So that's equal to sigma wi wj omega I dot omega j. And it should be pretty obvious that what we're going to do is take omega I dot omega j equal a new thing called gij. And that's the metric tensor but with contravariant components. So now if I want to take w dot itself, well that's wi wj, I'll write that again, omega I dot omega j, summed over I and j of course, which I don't need to say because of the summation convention, equals wi wj gij. So it's exactly the same as when we had a vector v in contravariant form, vi, vj, gij, except that we've got upstairs indices here to sum over with respect to the downstairs indices on the coordinates themselves. So let's just have a think about that. w dot w equals wi wj gij, and then if I take this in a bracket here, I can just call that w with a superscript I. So wi equals the dot product. So we can take a downstairs index wj and ij equals wi. We can raise an index. We can take an index from downstairs and make it go upstairs simply by multiplying by this thing here. That's great. Let's just think about this from a slightly different perspective. I've got wj, let's say gij, and that leaves me with an I upstairs. I might want to contract and bring it down again. I, let's say k, and that really ought to take me back to where we started from. So these things here, this thing here, gij, gij, summed over I of course, should of course equal the identity operator. And of course it does, because look, we've got this term here equals omega I dot omega j. And this one here is ei dot ej. That's that and that's that. No, I've got an I and a K, not an I and a J. It's easy to get this wrong. K. Okay, and of course that's summed over I. So I'm going to use the commutativity of dot products. I'm going to say that's sigma over I. Actually, I'm not going to write that down anymore. Omega j dot omega I. I'm just going to write it the other way around. ei dot ek. And then I'm going to bracket it slightly differently. J omega I dot ei ek equals omega those are vectors omega j that's just one, the term in brackets, times ek, that's a vector, equals omega j dot ek equals delta jk, as it should. So basically these two things here are inverses of one another, and if we want to calculate them, then the upstairs index, this thing is a matrix inverse of that thing there. So where does all this leave us? It basically leaves us with this nice ability to raise and lower indices at will. So we can raise an index and lower an index by multiplying by the appropriate metric tensor. So I'll just give you a couple of examples. If I've got a big I, J, K, L, I might want to lower the I and the J index down. So I'll multiply it by G. I want to contract that I with a I, J, K, L, M. And I might want to get rid of that J there. So it's J, K, L, M. I just want to make sure I haven't got any letters. And we'll call that F. The I and the J have cancelled from the top and the bottom. We've got a K, an L, an M, and an N. So we can lower using that. On the other hand, if I've got a tensor like this, K, L, M, where's my J gone? There's no J there. J, K, L, let's say I want to raise the J, the K, and the L. So I'll multiply it by G. Well, I'll put the G's in first. I want to contract the J, the K, and the L. J, K, L, M, N, O, I guess. And that will take me, I is as it was. The J and the K and the L have gone, and we've got an M, which is this one here, an N, and an O. So we've taken the 3 downstairs index to an upstairs index. And when we start fooling around with the Riemann curvature tensor, we'll see that we need to do all this all the time in relativity, so it's a useful operation. I'm going to stop there.